Hello, everyone. It's a pleasure to be with you. I'm sorry I can't be with you in person, but my name is Victoria Hutchison. I'm with the Fire Protection Research Foundation at NFPA. I hope you all are having a great conference. I'm going to be talking about guiding a fire-safe energy transition through applied research and NFPA standards. So the Research Foundation, for those who don't know, was established in 1982 in response to a growing need for research that better informed NFPA's expanding body of codes and standards. And to ensure research remained independent, the foundation was formed as a separate nonprofit organization. Since then, the foundation has facilitated major research programs, both domestic and international in scope, that address industry challenges in multiple areas of the fire and life safety world. Findings from the foundation's critically applied research have been used by NFPA's technical committee members and others to support the association's fire and life safety codes and standards and other activities for many decades. Globally, we're setting goals to achieve a cleaner, smarter, and more resilient energy system and achieve carbon neutrality by 2050 by focusing on reducing carbon intensity through expanded use of EVs, micromobility devices, expanding renewable energy capacity, and battery storage, pushing for highly insulated buildings to improve energy efficiency, while also supporting innovation. These are all critical parts of the energy transition, and while they're all exciting changes, it's not only a green energy transition, but it's implementing radical changes does not come without challenges, and there's many concerns to be addressed and knowledge gaps to be filled. It also brings with it a transition of hazard. We've seen tragic fires and insulated facade systems around the world. There are significant challenges with EVs, both cars and micromobility devices, and adding solar panels to roofs changes that hazard scenario as well. It's not that most of these systems are necessarily more dangerous than traditional fuels that we rely on, but the problem is, are we introducing new hazards and are we prepared for these hazards? To answer that question, we have to look back to how we got to where we are today. We look into our building regulations and codes, and what we'll find is that we traditionally design by disaster. Major changes in building codes and regulations are typically directly tied to major disasters that happened in a particular jurisdiction. But we are still seeing this today with key technologies associated with the energy transition. For instance, the Liverpool car park fire that happened in 2017 woke us up to the challenges that modern vehicle hazards may be changing. And is standard protection adequate? Looking at the Surprise, Arizona ESS explosion in 2019, kind of woke up the world to the potential explosion risks presented by lithium-ion batteries. And finally, the Moss Landing incident in 2025 in California in the U.S. really highlighted awareness to potential environmental and exposure impacts of battery fires. So as we're introducing new hazards into our built environment, let's not wait for disasters to happen. We need to learn from what experience has shown leads to disasters and apply that framework to the changing hazard landscape coming with the energy transition. This requires our collective global community to take a holistic approach to protection of property, people, and the environment. But to do that, the energy transition and sustainable designs need to be sure that they are aligned also with our fire safety objectives and that those aren't compromised. When we look at these tragedies in the past, it comes with an understanding that we need a new way of thinking, a more complete model for how safety actually works. So we developed that at NFPA in 2018 with the Fire and Life Safety Ecosystem. This framework acknowledges a simple truth that no single policy, product, or person can keep people safe, but safety only works when all the pieces do, when we develop and enforce strong codes and standards, when the workforce is trained and competent, when the public is informed, and when investment is made in safety, infrastructure, and in research. A framework was needed to help connect the dots, and the Fire and Life Safety Ecosystem does this. It includes 8 interconnected cogs, policymakers setting the right regulatory framework, jurisdictions using the most updated codes and standards, applying all of the standards, including the reference standards, prioritizing safety across the board, promoting the development of skilled workers in the design, installation, inspection, and maintenance phases, supporting effective code enforcement, and providing effective preparedness and response capabilities, and educating the public on the dangers posed by these hazards. Every cog is essential. When one or more elements of the ecosystem is missing or ignored, tragedies can occur. So let's take a closer look at a few of the COGS in relation to the emerging risks that we see coming from lithium-ion batteries. As technology changes, safety advocates constantly assess the risks as well as behaviors and actions that can create new hazards. The current editions of codes and standards incorporate learnings from recent research, technology advances, case studies, loss experience, and proven best practices. So looking at this from the energy transition lens and looking at NFPA's suite of around over 300 codes and standards, there's a number of codes that tell you what need to be done, standards that tell you how to do it, recommended practices or guides that can be advisory in nature. But there are a number of resources here from NFPA 1, the fire code, the electrical code, NFPA 70, to a new project coming from NFPA as in NFPA 800, looking at a comprehensive life cycle of battery safety. On the standard side, a few recognizable ones may be NFPA 855, the standard for energy storage systems, or 88A on parking structures, or 30A for dispensing facilities, or the 6869 suite for explosion prevention and control. So while we began with 855 addressing energy storage systems, now we're building on that with NFPA 800, which is the new standard under development that will address battery fire safety across the entire life cycle, from design and transport to storage, installation, use, disposal, emergency response. NFPA 800, the battery safety code, was approved in December 24 for the Standards Council for development, and a technical committee was appointed to begin developing a draft. Given the urgency of the issue, we're moving quickly on the standard, and we're expediting a provisional standard that allows us to disseminate what we know more quickly to help further advance safety. This provisional standard for NFPA 800 will be only the third time in NFPA's 130-year history that they're developing a provisional standard. But the technical committee just finished meeting last week to revise the initial draft of NFPA 800, so stay tuned for more information soon, and you can follow along nfpa.org/800 or get involved in the process. The next COG is investment in safety. And a key element of investment in safety is doing research, gathering data, analyzing information. And this is an investment that is fundamental to our work, particularly at the Fire Protection Research Foundation. So let's dig into a few examples of how we're contributing to safety and updates in codes and standards with the research happening at the foundation. So our portfolio in support of the energy transition focuses on a lot of things. A few dominant areas in that portfolio is around lithium-ion battery fires, electric vehicles, electrified transit fleets, energy storage systems, and then other technologies like PV, hydrogen, and others. We generally focus that portfolio around general hazard characterization, so defining the hazard and understanding of the risks, assessing their impact of that hazard in the infrastructure, and then looking at emergency response consideration. So we're going to start digging into some of the key questions that we get asked and the research that we're doing to support that. So here I mentioned earlier, parking garage fires are becoming a lot more intense, large loss incidents. We're seeing structural damage, we're seeing collapse, we're seeing multi-vehicles being involved up to thousands at times. So let's beg the question, has the hazard in modern vehicles changed? And beyond that, how does a combustion engine vehicle compare to an EV? So digging in very fundamentally, have these vehicles changed over time? Yes, largely driven by the increase in plastics. So plastics have approximately doubled over the last few decades of the percentage in vehicles. Their weight has stayed about the same, but that's because they're getting larger. We're using more materials. We're just using lighter weight materials. We're also introducing new fuels, such as battery packs, such as the EV evolution continues. But those changes, coupled with the fact that our cars are being parked closer together, we're placing them in denser configurations and parking systems and the stackers and the automated systems, this changes the landscape of the hazard. So let's take a look at a few. So we are doing some testing that's been ongoing in partnership with RISE and RISE Fire Research to compare ICE fires to EV EV fires and overall compare that hazard. So you can find more resources and follow along with this research using this QR code. But overall, what we found through a couple phases of literature and through full-scale testing is that overall the hazard is generally comparable when you're dealing with the same vehicle class. There's typically an average of around 6 to 8 for a smaller standard passenger vehicle, average heat release rate in that range. Obviously, when the batteries get involved, there are very unique dynamics to that. But what we found was that the larger vehicle size actually impacts that hazard much more significantly than the fuel type from the testing that we've done to date. For instance, the passenger vehicle EV was around 7.5 megawatts in our testing versus a passenger truck was around 19 megawatts. So that definitely has an influence on the hazard beyond just the fuel source. From both an ICE or an EV fires, you can get very intense heat flux, which gives you a high potential for fire spread if you do not have sprinkler protection. We did find the heat flux to be a bit higher with the ICE test than the EV, but both had levels of heat flux that would make it likely for spread without sprinkler protection. And the other important thing is the high ceiling temperatures from both vehicles were sustained around 800 degrees Celsius at the ceiling, which presents a potential structural integrity and spalling issues due to the long exposures of those. So what's happened in the codes and standards? So looking across the board generally in response to the incidents and results of recent research from the foundation, many of the standards have moved the hazard class of modern vehicles up a class in terms of the level of protection required and the overall hazard classification. Another big change is in NFPA 88A parking structures standard. Sprinklers are now required in all garages in response to some of the latest knowledge on this topic. But the other thing is, as we increase density of cars and parking structures, the question is standard protection that appeared to be adequate to achieve control at the single vehicle level, could that be appropriate if you do a 2-car vertical stacker? So not doing retrofit of the system, but putting a stacker into a standard garage with existing protection. What does that look like? So here, I'll let this video play here. So I will note that this is below what NFPA standards currently have required. Standards require a higher water density delivered at the ceiling only, upping it a couple hazard classes or requiring sprinklers at each level. So what we found was that the protection that's required for just single vehicles in standard garages that we tested at the single vehicle level, that was not adequate. We activated all 9 sprinklers within about 10 minutes. A few minutes after that, within 15 minutes, all of the sprinklers beyond the perimeter would have activated as well. We were unable to obtain control, and we ended up losing the underpan of the battery pack and the EV on top, and the battery started falling on the car below, kind of further intensifying the fire. So a lot of challenges there to address. This is kind of what is currently in the standard for levels of protection, but there is a lot of changes and guidance coming in the upcoming edition of 88A, so you can use this QR code to follow along with those updates. And there'll also be additional testing and research coming from the foundation to address this hazard. Continuing on with electrified vehicles, we're now also electrifying bus fleets in significant quantities. So taking depots that maybe traditionally use diesel or other fuels, now electrifying those. So how do we safely adapt protection for electrified bus depots? So the big concern when you look at what is the significant concern in this transition is if we have a fire in one bus, what is the potential of it spreading to multiple and getting to a level of a catastrophic event? So there's differences in, some incidents it was charging, some it wasn't. These buses in this incident here were actually decommissioned, but you can kind of see the impact of how that spreads. So At the foundation, we've been doing a lot of work in collaboration with some other universities, University of Texas, Austin, Ohio State, Energy Safety Response Group, and others to study kind of the impact, looking at incidents, modeling some of these incidents, looking at speed of fire spread, fire development within the bus, understanding atmospheric exposures, gas release, all of these things that impact safety within the depot, trying to characterize the overall heat release rate to inform overall, what are the threats present within the depot, what consequences are we trying to prevent, and what barriers or mitigation strategies can we put into place to minimize the overall risk and consequences here. So we did this work for the Transportation Research Board to develop a guide for lithium-ion battery transit bus fire prevention and risk management for transit agencies, manufacturers, battery suppliers. And the core of that was developing a hazard mitigation analysis and developing a framework and kind of a decision-making framework for how to assess the hazards at your facility, what tools and resources you can utilize to assess that, what barriers you can put in place to minimize your overall risk. So you can follow along for those deliverables at that QR code there. And then the rapid adoption of EVs is also driving the need for extensive charging infrastructure. So EV charging stations are increasingly being co-located with traditional refueling stations like gasoline or hydrogen stations. And both types of infrastructure are crucial for the energy transition, but their proximity introduces potential safety risks. There's a lack of comprehensive safety guidelines that address the unique risks of placing EV charging stations near refueling stations. So there's been a lot of debate in NFPA codes and standards around this, where this guidance should live. And the outcome of that was that where charging equipment can be located and where charging can occur at motor dispensing facilities, that is within the scope of NFPA 30A, which is the code for motor fuel dispensing facilities and repair garages, and the installation methodology and standards for EV charging equipment are in our electrical code. But as they're writing new regulations around safe siting, there's a number of questions that came up, like what's the hazard classification of the charging station? Who decides if it's a hazardous location? Does the cord create an EV, to the EV create a hazard? Is there a chance of arc flash, or what's the potential for sparks or other ignition risks? So there's a number of questions that need to be answered to understand the hazards. So the foundation is currently engaged in conducting a comprehensive risk assessment to determine the safe placement of EV charging near these other refueling stations, and we'll be providing recommendations to the applicable committees. As the rise in DC electrical equipment increases, worker safety must also be kept top of mind, as arc flash risk is an increasingly important issue, needs to be better understood from the DC equipment side, and how do we calculate that risk to personnel working on this equipment. So we're currently fundraising for a new study to develop a mathematical model for designers and facility operators to apply in determining arc flash hazard distance and incident energy to workers, and what they could be exposed to during their work on electrical equipment. Currently, the guidance in IEEE 1584 is only limited to AC electrical systems. So there's a need to develop this guidance for DC applications, as this is really expanding in use through the energy transition. So this is getting underway, and the learnings and feedback will feed back into the electrical safety standards and programs at NFPA around maintenance, electrical equipment maintenance and electrical safety for workers in the workplace. Another key question is, what is the appropriate separation distance between battery energy storage units to prevent fire propagation? So this is something that has been a question and something that's come up in 855 discussions for many years now. But the challenge is, if we have one incident ongoing, how do we minimize the consequence and ensure that it doesn't propagate to adjacent units? So when we look to 855, what the original guidance was in 2020 and 2023 editions, we see that the guidance was to keep the maximum stored energy to 50 kilowatt hours each, and space them at 3-foot separation or from each other, otherwise go to large-scale testing. And this was validated in a previous study conducted by the foundation. But as we're seeing in 855 in general, we're really pushing towards the use of large-scale testing to validate this performance for the given product that is being installed. Also wanting to account for wind or environmental conditions and verification from a registered professional to ensure that propagation to adjacent enclosures will not occur. But to further support this, the foundation is working to inform standardized spacing practices for various lithium-ion-based products, whether that's energy storage, EVs, electrified fleets, based on analysis of experimental data and validated computational modeling to provide practical recommendations back to the committee to help prevent cascading failures and protect adjacent assets. So another hot topic, as more and more batteries are coming onto the marketplace, and we've seen more incidents, is what is the environmental and health or exposure impacts of lithium-ion battery fires compared to other common fires. And there's a range of questions that come up of what is the environmental impact, or what is the gaseous exposure to the air. What's the impact on firefighting activities on the water runoff or in the soil? What is the deposition from the fire to the soil? What's the ecological impacts? But also, what is the impact on the public? Are evacuation zones required? What is the exposure to the fire service? What is the contamination on their gear? How is that getting into their bloodstream, or is it? So a lot of questions on this front that we're looking into. So we're looking at both the toxicity side, which is the impact on humans or living organisms, the acute and chronic health effects, and also looking at the environmental impact, which is looking at air, water, soil, ecosystem, which you can see the details there. From some of our research that we've done to date, we found that carbon monoxide and carbon dioxide emissions from lithium-ion fires are comparable to classic fuels. HF and the metals coming off of these fires are kind of key identifiers, even though the HF is very reactive and not detectable at very far distances. The total emission of soot from lithium-ion fires is typically lower than typical hydrocarbon fires, but the particle chemical structure does differ, especially because of the metals. The volatile organic compounds from lithium-ion batteries appear to be similar to classic fuels, yet the PAH emissions do appear to be lower compared to common fuels. So there's a number of parameters that influence the impact. There's also a webinar and other resources available on this. And there continues to be a lot of testing, research, and data that we're doing from the foundation side to continually evaluate the impact, of battery fires in runoff water, gaseous emissions. Both of recent testing have shown some favorable results, with gaseous emissions being lower than the IDLH level, and water runoff values being better than expected, but more results to come on that front. But we're also looking into the exposure to the fire service. So when they respond to a fire involving lithium-ion batteries, what is the exposure? So we're capturing the exposure from recent EV firefighting tests. We're also doing smaller scale with micromobility scooters, leveraging from real incidents at energy storage fire exposures, analyzing the contamination, and then doing several different cleaning methods to evaluate efficacy of the cleaning procedure, and looking at how far through each level of gear it gets, and the cleaning procedure for each of those levels. also looking at what is the exposure to the fire service in their bloodstream, so doing some biological testing there as well. So more to come there on kind of overall impact of these fires on health and environment. The last cog of things I want to address is preparedness and emergency response. So providing, as we know, there's a myriad of disasters that the first responders have to respond to. So from car crashes to medical emergencies, natural disasters, and now with these battery fires, first responders, they're the first line of offense and also defense. So they must be well trained, well resourced, well prepared to meet the varied needs of their communities. So on the first responder side, NFPA has developed critical resources, including emergency response guides for EV battery incidents and multiple training programs to better equip fire service professionals. So there is not only for the fire service, but others in that value chain, whether it's secondary responders or insurance adjusters or those working at dealerships, what they need to know about these. There's lots of resources. Here you can go to nfpa.org/EV to get access to all of the training programs NFPA has to offer. But a critical piece of the training is making sure it is up to date, understanding what the needs are from the fire service, and that we're answering those questions and keeping the training up to date with the latest information and knowledge. So what we have been doing over the past couple of months is a lot of large-scale fire testing with full EV battery packs across different manufacturers, and also full-scale vehicle tests. So we looked to the fire service for what different tools or tactics that are emerging that they had interest in potentially using or would like to see validation of. We've done a lot of testing to evaluate these different tools, provide learnings and considerations that the fire departments can take back to inform potential updates to their standard operating procedures. How do we optimize the time and the resources required to manage EV incidents? What are critical learnings or hazards or warnings that we may need to be aware of when using some of these emerging tools? So there's a lot of resources coming available, webinars and full reports documenting this information. And we will also be sharing our learnings in new micro-learning training modules released from the NFPA training program. That'll be available later this month. We'll be looking from everything from size up, rescue and rapid extrication, to all the different tactics, tools that can be utilized here, and then also post-incident operation considerations as well. So you can go to this QR code here and get resources for existing training and upcoming. So this wraps up the technical part of my presentation, but if you have interest in accessing some of the codes and standards mentioned, you can get digital access through NFPA link here. If you want to get involved in the codes and standards process, that is an open process, open to the public for comment. Anyone can join a committee. So if you go to this red QR code, you can see a video on how you can get involved in that process. From the Research Foundation side, we're constantly wanting to hear from stakeholders to learn what the needs are and make sure that our portfolio is reflective of the needs out there. So feel free to read through some of the reports mentioned or submit a new project request. And there's also plenty of NFPA training and public education materials available at nfpa.org/EV. And with that, I thank you so much for your time and attention. I hope the rest of your conference goes great. And I hope this was enjoyable. Feel free to reach out to me at my contact information below. Thank you so much.